Okay, what is 10 plus 20? If you said 30, you'd be correct. Now, what is 1 plus 2? This is a trick question. But if you said 3, you'd also be correct. Fabulous. Now, what is 0.1 plus 0.2? And the answer is 0.3. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 4. That's weird. Where did that 4 come from? Okay, let's break this problem down a little bit and start with the fundamental block, numbers. How do computers know what a number is? In a lot of human number systems, we use base 10 to represent numbers, meaning there are 10 unique digits from 0 to 1, and each column represents an amount of a power of 10. Take the number 10,367,807. This number has 7 amounts of 10 to the power of 0, 0 amounts of 10 to the power of 1, 8 amounts of 10 to the power of 2, and continues like this up until 1 amount of 10 to the power of 7. Add all those numbers up and we end up with our original number. Counting in base 10 isn't inherently human. Historically, some societies counted with base 12 because it's got nice and easy factors. 6s, 2s, 3s, all of those. But the reason 10 stuck is because we have 10 fingers. So maths is a little easier for our monkey brains. Computers, however, they are not monkey brained, nor do they have 10 fingers. What they do have is electricity, or a lack of it. This brings us to binary. This is a system of counting numbers with only 2 states. So instead of having 10 digits to quantify different powers of 10, we have 2 digits, 1 and 0, to quantify different powers of 2. Let's take the number 164. Okay, so we're going to work backwards with 8 bits, meaning 8 different digits, literally a binary digit bit. So starting all the way at this end, if we do 164 minus 128, we get 36, which is positive, so we put a 1. Then working our way down, we do 36 minus 64, in which we get negative 28, which is negative, so we can leave that as a 0. Then we do 36 minus 32, which is a nice positive integer of 4, which means that's a 1. 16 and 8, when subtracted, would give us a negative number since they're both bigger than 4, so they just both get a 0. When we get to 4, subtracting it leaves us with exactly 0, which means this bit fits perfectly, so we mark it as a 1. At this point, there's nothing left to subtract, so all the remaining lower bits are also 0. This number system is just as valid as the decimal system and can also represent an infinite number of numbers given infinite memory. One isn't inherently better than the other. What isn't infinite, however, is memory. If we want to represent numbers smaller than 1, say half, we need to extend our number of bits to the right of the binary point and keep reducing the exponentiation factor. Ooh, that was one hell of a word. So we get this, a column for 2 to the power of negative 1. Ooh, with negative exponents being simplified into this fraction, making it half. You've probably already noticed the issue with this, but let's make it even clearer by showing 164.125. I'll give you a second to think about it. Correct! By being more precise with my numbers, I use more bits. If I wanted to represent 1 plus 2 to the power of negative 10, I'd need 11 bits alone to represent such a small number, which is fine when, writing it down. But when doing computation, it doesn't quite work as memory is super limited. This led to something called floating point binary, where instead of making the number of bits for each number depending on the number that's stored, and no one really knows how many bits are in a number, all numbers can be stored in, for example, 64 bits, like in Python, give or take. And then we play a balancing game between accuracy and size. If the decimal point is over here, we get a super big number, but not very accurate. Whereas if it's over here, we can represent a very accurate number, as long as it's not too big. The value that determines how much to move this decimal point by is called the exponent, and the bit storing the number itself is called the mantissa. The exponent is usually stored in 2's complement, which is a way of representing negative numbers in binary. However, we won't be getting into that today. That'll be for another time. Individually, this would never cause any problems. 0.1 and 0.2 are both small numbers, not needing very many bits to represent. Right? Right? So what actually causes the 4? Let's represent our problem in binary since we now know how to do that. We can then debug from there. Okay, so 0.1 into binary, starting off 0.5, obviously that's too big, that's a 0. 0.25, that's also too big, that is also a 0. 0.125, still too big, so 0. 0.00625, okay, that's small enough, that leaves us with 0.0375. Next, 0.03125. Okay, I'm using fractions from now on. But yeah, that's small enough, leaving us with 0.000265. Perfect. Next, we have a 16th, which is just too big, 128th, which is too big, a 256th, which is just small enough, and then 150/12th, which is also just small enough, however, not quite. Did this guy just say 150/12th? Damn, I'm tripping. I meant a 512th. And yeah, that's the thing. It never actually ends. In the same way we can't fully represent a third in decimal with a finite number of digits, 0.1 cannot be represented using a finite number of bits. And guess what? Neither can 0.2. Computer memory isn't infinite, so it does the next best thing, which is representing the closest possible number to 0.1 and 0.2 that it can, before just giving up, meaning the bits being added together aren't exactly 0.1 and 0.2. Instead, they're numbers super close, but not quite, which results in a different output and how we ended up with our stray 4. However, final plot twist, 0.3 also can't be represented using a finite number of bits. So even if there was a magical way to do 0.1 plus 0.2, the final sum, 0.3, wouldn't be able to be represented either. So yeah, floating point maths in computers is really just making a lot of rounding and hoping it doesn't cause major issues down the line. Most of the time it works well, thank God, but other times you end up with the easiest question in computer science to get wrong. Anyways, thanks for watching. Bye.